Okay, so yeah, in this lecture, we'll deal with the subject of compound interest. First, we want to contrast compound interest with simple interest. And as you can see here, simple interest, it grows linearly, right? While compound interest grows exponentially. We're not going to focus on simple interest much. It is still used in some businesses, right? Um, while compound interest is mostly used, especially in the banking industry, right? Where money lent to you, the interest is calculated using compound interest approach, right? Formula. If you were to place money in the bank, right? They will pay you interest that is compounded or calculated compoundedly, right? Um, the difference though is that, and you probably, some of you probably know that the interest they pay you is a fraction, small fraction of what it charge you if they were to lend you money. And the reason being is that, well, banks are there for profit. Eh? Yeah, banks are there to profit. That's the first thing. And then they also factor in things like inflation rate. You might put your money in the bank and in a year or two, you can draw it out. But when a bank lends you a couple well $1 million, they you might say, well, look, you want 15, something 25 years to repay a loan, right? Now, because inflation can take place a whole lot over that period of time, right? Think of Guyana here. We have suffered nearly 100% inflation from COVID to now. Things have doubled in prices, right? You notice that? Things have gone up drastically. So the bank usually have to consider what they call, um, well, nominal interest, and then they'd have to talk about effective interest, right? So normally, a nominal interest is what they tell you, right? But then that's not what they will get. Let's say they tell you 15%, but inflation rate over so many years is 10%. So the effective rate really is just 5%. I'm treating it linearly, right? Yeah, so sometimes that's why they have to charge so much, right? Besides profit, right? Besides the idea of profit, they have to consider things like inflation, right? Which affects us terribly, especially here in Ghana, right? Because the government has very little control over inflation. They do nothing virtually to deal with inflation in this country. Right? But let's then get into that as politics and so. That's another course. Right? Just to illustrate the difference between the two. So here's some money, $1,000 invested over this going to be about a 20-year period, right? And this, put on my annotation. Yeah, this blue line here is the value of your investment when it's calculated, when the interest is calculated using simple interest. So you have a linear increase, right? A linear graph. However, if you were to use some kind of compounding, right? As you can see here, your investment will grow exponentially, right? I think in our country here, banks usually when they when you put money in the bank, maybe fixed deposit or you have a savings account, they normally compound the interest quarterly, right? But when you lend you money, like I have a credit card with Scotiabank, when you owe them money, if you buy something or you take a cash advance, they compound the interest daily. So they're brutal, right? And they're giving you money, they're doing it slowly, quarterly. When you owe money, they have to charge you interest. They do it daily. You see? So those are things you have to check. If you take a long-term loan, if you buy a house and you take a mortgage from the bank, you want to ask, how are you compounding this thing? Monthly, quarterly, yearly? You need to find out that, right? From bank to bank, that may vary, right? Yeah. So that this gives you an idea that whenever compound interest is involved, right? The growth of the interest is exponential. Right? Keep that in mind. That's why it's so popularly used in business, as people want to multiply their investment quickly, right? Especially so banks. Yeah. How do we calculate? Oh, let me erase all of this. Yes, so this is the formula. This is the formula. Um, FV is the future value, in time, how much your investment will become. It's equal to the present value, right? How much you put in the investment, times 1 plus I. They explain that I is the periodic interest rate, right? So if they tell you, let me do some calculations with you. If they tell you the interest rate per year is, let's say, 4%, that's not what they're putting in here, right? You have to divide it by the compounding frequency, how many times per year they're giving you interest or charging you interest or what, right? And the N here, you see the number of compounding periods, which is this here, right? Um, yeah, so keep that in mind. Is the frequency, the compounding frequency per year times the time, right? That's the formula they use. And the actual interest that you'll earn, that makes sense. What money has accumulated minus what you started, right? So those are the formulas you'll need. This formula, in fact, is a little, well, not everybody like it because you have to calculate all these things before you put it in there. Let me erase it, these writings on my slides. And I'll show you another set of formulas that some people like more, right? And some people like it this way. So where you put in the rate of itself that is given, right? The rate of itself that is given, right? And the time there, right? So if you're compounding by the year annually, this is what you use. If you do it semi-annually, you stick a 2 there and a 2 there. Quarterly, you stick 4 there, you stick 4 there, and so on. So some people like this form of the formula. Right? It depends on which one you use in your calculations, and so over and over and over, you get to like one of them. I personally like these here. But the writer of the textbook that I'm using, he doesn't like it. I took this from somewhere else, right? Let's do an example or two, right? So here's an example. So this person invested 25,000 for 5 years at 6.9% compounded monthly. The bank don't get that here, but this is just a hypothetical situation. So you want to know how much was the accumulated value after 5 years and how much interest was earned, right, during those 5 years. So we have to do some preliminary because we're going to use that formula with the N and I and so inside. So yeah, that's what you put in. This is the nominal interest, right? That's the interest they read to you when you go to borrow again. Interest is compounded monthly, so compounding frequency is 12, right? The investment term is 5. Periodic interest then is going to be that over that, which is 0.575%. The number of compounding periods will be this, right? The 12 by the 5, which will give us 60. Right? So after we have found all of that, we now can, again, I have to erase all of this. We can now put it in our formula. And we'll end up with roughly what they have there, $35,264.89, right? And I talked about money. You always want to round to within a cent, right? From that, person put in 25,000, and they now have $35,264.89. So the interest rate will be the difference of the two, right? Which is $10,000, right? Again, always when you're dealing with investments, you want to compare it to, you put this amount of money in the bank, and after 5 years, that's what you get. You know, people might think, well, why not try another type of investment, right? Keep that in mind. And they say most rich people don't put their money in the bank. They find more profitable ways of investing. All right, so let's take one. This is a little harder. What has happened here? And this can happen in real life. You put money in the bank and the interest rate change. Like you can get greater, you can get less, right? Over time. So this person initially noticed the interest rate is 6.5% for a few years. So after 4 years, it went down to 4.4%. You see, so they're giving the person less, right? They're giving them less interest after the 4 years. So simple, you'll have to take this problem in two stages. You have to calculate, well, how the investment will grow for the first 4 years. Then that future values become the input or the present value for the second portion of the investment, right? And then you'll calculate, do another set of calculation to find the value of it for the rest of the years that you have it in there. Good. So with that now, do it in parts. So for the first 4 years, you do your calculation. These are all the information given, right? Let's say this is the nominal interest, the frequency with which is going to be compounding, years, periodic interest, the number of compounding periods, and we put all of that, we get this. After 4 years, that's what you get. Notice the little suggestion, don't round it, don't hurry to round, right? We'll leave a couple of decimal places. And then you take this now and inject it into another period, right? You inject it into another period. I think this is very disgusting to have to erase everything. Yeah, so you put it in the second period now, you do the same calculation. What came out of the first 4 years is now your present value. The nominal interest has dropped. The frequency of the component is 4, right? The time period, 3 years. So you find the periodic interest, the number of compounding periods, and you put it in the formula, and you get this value, right? So the amount that will accumulate after how much years is that? 7 now? 7 years is going to be this. You started off with this, you end up with this. So total interest over 7 years is that, right? I'll send all these calculations in a PDF document, so you can always spend some time with them. If you have any questions about it, that's what the tutorial period is about, right? We're not going to be doing additional examples in the tutorial period. Y'all are too many. So what will happen is, if anybody don't understand how we do a particular piece of calculation, well, to clarify it then, right? Let's take another simple one. In this case, the person is using the formula I said I like, right? So I like this form. If you notice how much less you'll have to do in this one, right? So an investment of 3,500 after 2 years. You want to know if it earns 1.5% interest compounded quarterly, right? So your time, 2 years, 3%, right? So what's that? The rate is 1.5%, right? So you divide that by 100. M is the number of times they're going to compound the interest for 1 year, right? So 4 is the answer. You put all of that in here. P, 3,500. R, and that's the 0.015, divided by 4 as the number of times they'll compound the interest. And then the 4 by the time again, right? And you get $3,606.29. So this way, using this formula, the calculation to me is more efficient, it's faster, less work you have to do, right? Take another one. And this is a common question sometimes you hear people ask. How many years will an investment take to double if they're offering a 5%, whatever they offer, but in this case, they say 5, right? So if you know a bit of algebra and logarithms in particular, this is easy. This is easy, right? So look at it good. So we have the formula. You make an investment P. We don't know what it is. We just say any investment. All we know is the interest rate, right? And this one is compounded annually, right? So our formula is, well, M is 1. M is going to be 1, right? Yeah. So if our investment is going to double, right? Yeah, if our investment is going to be double, so if you start off with P01 to P, right? So we put all of that in the formula. If we take this P over here and divide, we will get what? Well, okay, before they do the division, we simplify this. And 1 plus 0.05 to the T power, that's what we write back here. So you divide through by P and you get 2 equal 1.05 T. So how do we get T? Because that's what we want. How many years will it take to double our investment? Right? That's what we want to know. So we have to know a little bit of logarithm. So you can either use log, but in this example, the writer used ln, right? Remember I told you about ln? So you ln both sides, right? You ln 2 and you ln 1.05 to the T. Remember that rule I gave you in our force lecture, right? And you ln or log. I mean, use log or let's say a to the b power is equal to b log b, right? So you just take this power and bring it down to the front here, right? That's what happened here. You can take this t to the front, t ln 1.05, and that's what's happening here, right? So ln 1.05, the calculator is going to give you can take that across and divide it in 2, right? And you will see that you will get roughly 14.2 years, right? So they say a little more than 14 years the investment is going to double, right? And this calculation can be adapted and changed to if you want to know how long will it take to triple your investment and all kinds of things, right? Lots of things can be varied in the question. There is a thing around the internet you can watch. They call it a law of so for it to be easy, they say law of 70s, right? 70s. Sometimes they say law of 72, where they show that good. So sometimes you in your calculation, it's you don't want to just know the future value, but maybe you give and this is more for mental exercise. Really. You you give them the future value and you want the present value, or say, look, in so much years you're going to get this. How much should you invest now to get that? Those are more hypotheticals, like, right? So here you have present value equal to the future value divided by 1 plus I to the n. And mind you, this is a little bit of algebra, right? If you know your algebra, this shouldn't be hard to derive. As an example, this is an example here. So if you have calculate discounted value or the present value, then if this is the future value, 4,320, that has accumulated over 5 years, 8 months at this interest rate, right? So, so putting it in the formula, you know that the interest rate for annum or for year is that the interest is compounded monthly, so 12 is what is the compounding frequency. The time is 5 years, 8 months. So 8 months is 8 over 12 years. Periodic interest, you have to divide this annual value that is given here by 12. So that's it. The number of compounding periods is going to be it's the frequency of compounding by the time, which is 12 by 5 over 12. You get 68. You put out the formula, and you will get. But I think they write the formula differently here. I think the formula I gave you previously is FB over 1 plus I to the n, right? So yeah. It's the same thing. It's the same thing. You know your algebra, you know what I'm talking about. Right? Yeah. So let's take this one also. Maybe you want to calculate the interest rate. You're taking the same compound interest formula there, rearranging it to get I, and from I, we can now get the capital I, right? Capital I, interest for a year, right? Yeah. And this formula was, well, it's a rearrangement of another one we had already, right? The beginning of the lecture. So a little problem, maybe an example of it. This person invested some money. It grew to 33,500 over a 9-year period. You assume that the interest in your account was compounded monthly. You probably find that out. What was the monthly interest rate? What was the annual interest rate? I can tell you to give your answers a percentage wrong it to 2 decimals. So this is what we know. Put in 4,900. Go up to 3,500 over how many years? 9 years, right? It's compounded monthly, so the compounding frequency is 12. Yeah, you got it, 9 years. Number of compounding periods is going to be COY 12 by the 9 years, which is 108. And we put that in our formula. That was given in the previous slide. You get I being 1.80% per month, right? That's the interest per month for the periodic interest. I'm hoping that all of us can use our calculator to have something like this here. If you have, something to the 1 over 108 power. You might have to play around with your calculator to get that, right? So after you've done that, you want the nominal interest, what we call the interest per year, right? So we use this formula and you get 21%, 21.55%. Good. So this is another twist to the, remember we talked about effective interest rate, right? Because sometimes you have two investments and you want to compare them, right? You want to compare the investments. So this is a bit of algebra, right? It's a bit of algebra. And the effective interest rate is given by this formula here, right? So if you have two investments, use this formula because the I is going to be different, the C is going to be different for the two investments, right? This is a bit of heavy algebra. They're showing you how to do it really, right? If you see, they say give the same principal, time period, effective rate, and so on, right? And maybe you have two investments. One of them is compounding, maybe semi-annually. The other one annually, right? But certain other things are different. Well, use this formula to find the effective interest rate for each investment. If they're the same, well, then you can safely say, you know what, I'll get the same amount of return if I were to use them, right? Or you can know which one is a better investment. You know which one is a better investment. That's sometimes all the numbers seem to puzzle you. So how do I know which one is a better investment? Well, it's good to calculate the effective interest rate of each, right? And see. So a quick example. So just remember that formula. So you have this story here. You have an investment at 6.4% compounded quarterly. Express your answer as a percent. Okay. Yeah. While you're calculating the effective interest rate. So quarterly, so C is going to be 4. Nominal rate is 6.4, right? The periodic interest is this. Right? So you put in the formula and you get 6.5552%, right? Roughly 6.56, right? And the reason why this is the effective interest rate, even though they tell you 6.4, it's going to be a little more because after a quarter, they add on a little to how much you have in terms of interest. And the new interest is calculated from that sum, right? So that's something to think about. So even though you might bank tell you you're going to get 6.4, you get a little more. You get a little more. Don't rejoice over that because when they lend you money, they do the same thing. Their effective interest rate is much higher. Maybe I'll give you one of those questions for a test or so, right? Where you borrow money to maybe build a house and so on. And they tell you a certain amount of interest. But what's the effective interest over, let's say, 10 years or so, right? Yeah. Again, now if you have same compound interest formula, we're analyzing it to find the compounding period and time, right? So we're going to do some algebra here. Really, they want n. From n, we can do stuff with it, right? So you bring the PV over, divide this. Then you lim both sides, and you get this formula. N equal ln of FV over PV, all divided by ln of 1 plus I. Right? So from that now, you can get your T. Right? T will be equal to N over C upon Y. And this formula was used already. You were using N equal C over Y, but sorry, compounding frequency for you times time. We're using a formula. So once you get N, you can get T. Right? A little example with that. So you want to know how long will an investment of 24,000 grow to at least 96,000 at 5.8% compounded semi-annually. So they want you to express your answer in years, around the 2 decimal place, years and months, and then years and days. Just we're gonna just take the part in years, right? So they give you all this information, how much you have, how much you expect to get semi-annually. So C is 2, nominal interest 5.8, periodic interest is that divided by 2 is 2.9. So substituting our formula, and we have n equal 48.493. They tell you to keep a few more decimal places, and then you use the formula T equal n over C, which is that divided by 2, you get 24 years. Right? You can look at how they convert that to what do you want? Years and months and years and days. That's arithmetic, right? You do that to tickle your brain. Right? All right. So we'll stop there and then we'll continue with another topic next time.